This video serves as a segue between path analysis and multiple regression and structural equation modeling. We'll first examine what a possible model may look like in path analysis, and then see how structural equation modeling can add some flexibility and some powerful tools to our work. Let's say we have 4 variables. Our outcome is first grade reading scores. Our first predictor variable is parent education, which we feel predicts each of the other 3 variables. Our second predictor variable is school readiness when children enter kindergarten, which we feel predicts each of the other 2 variables. Our third predictor variable is school quality, which we feel predicts grade 1 reading scores. Here's a correlation matrix for these variables. We see that all 3 predictors are correlated with grade 1 reading scores, with values ranging from an R of 0.24 to an R of 0.42. We also see that the 3 predictors are all correlated with each other, with values ranging from an R of 0.2 to an R of 0.5. Because every variable is successively a predictor of every other variable, this model can be estimated directly using a path analysis approach through a series of multiple regression analyses. When you do path analysis in multiple regression, each of these paths is required to be there. Every variable is in some way related to every other variable. It either has a path leading from it to the other variable, or from the other variable leading to it. The path may be small, but it has to be there. That's just the way the multiple regression works. For example, what if we don't think that school readiness has a direct impact on school quality? Note that this doesn't mean that school readiness and school quality are uncorrelated. They may both have a spurious correlation through parent education. If parent education leads to both higher school quality and higher school readiness, there may be a spurious correlation between the two. What we are talking about here is proposing that school readiness does not have a direct effect on school quality. Similarly, we may feel that it is even less likely to think that school quality has an effect on children's school readiness when they entered kindergarten. They haven't been in the school yet to benefit from the quality. In this case, our model looks like this. Notice we have no arrow at all between school readiness and school quality. Remember, arrows between variables allow for there to be some effect. Maybe a big effect, maybe a small effect. But by including that path, it allows for some effect between the two. In contrast, when there's no arrow between variables, the direct effect between these 2 variables is required to be equal to exactly 0. We can talk about this as constraining the path or forcing the path to be equal to 0. Now remember, in path analysis, we used all of the possible paths and all of the correlations to come up with estimates for each path. We let the math do the talking and estimate what each possible path was based on the correlations. In essence, we could calculate each path based on the correlations, and based on the paths, we could go back and recreate exactly what the correlation matrix looked like. It's like the paths and correlation matrix kind of fit each other perfectly. But now, we've gone and constrained one path and decided that it must be equal to 0. That kind of screws up the math. If our model was valid before, we are almost certainly not going to be able to come up with path coefficients that will exactly reflect the correlation matrix anymore. Instead, we'll end up estimating path coefficients that can get us as close as possible, but they won't exactly recreate the correlation coefficient matrix anymore. Now, this may sound like a bad thing, but we'll see in a minute that there are some real benefits from not being able to exactly recreate the correlation matrix. Returning back to our example, here's our model where we constrain the path between school readiness and school quality to be equal to 0. And here's the correlation matrix based on our hypothetical data. This is the real correlation matrix based on the data in our example. We can use these correlations to estimate the paths in our structural equation model with the constraint or requirement that the path between school readiness and school quality has to be equal to 0. We can then use those same path coefficients to go back and try to recreate the correlation matrix. If our structural equation model included all of the possible paths, such as path analysis and multiple regression, we would be able to use those path coefficients to exactly recreate the correlation matrix. But because we've constrained one path to be 0, the question is, how well does our model allow us to recreate the correlation matrix now? We can think of this as evidence or lack of evidence of how well our model actually fits the data. Here's an illustration of what we might find. Notice the real or observed correlation matrix is what we saw in our raw data. Ideally, our results from our model should be able to reproduce the correlation matrix that looks a lot like this. If it does, then our model fits the data. It fits reality. If it doesn't, it tells us our model does not seem to accurately reflect what we saw in the world. So, how did our model do? The reproduced correlation matrix is what the model says the correlation should be. The better the model, the closer the reproduced correlations will look to the actual correlations. Sometimes the reproduced correlation matrix will look pretty good, but one or two specific correlations may be way off. That's an indication that the relationship is not being adequately reflected in the proposed model for those specific variables. There are a variety of measures called fit indices that use different ways to compare what we expect to see based on our model with what the data really show us. These indices can provide us a way to describe how well the model fits the data, often in a more understandable scale, such as a range of 0 to 1. Some fit indices even allow you to compare two different models in order to determine which is the superior fit, meaning which model fits the data the better. You can't do that in multiple regression because path analysis in multiple regression requires all of the paths to be there. For example, a minute ago we considered this model where we constrained the path between school readiness and school quality to be equal to 0. What if someone else proposed a different model where they felt that the effect of parent education was entirely indirect? What if they proposed that the only effect parent education had on first grade reading scores was through school readiness or through school quality? In essence, they'd be proposing that this path does not exist. They're proposing to delete it from the model or constrain it to also be equal to 0. The question then becomes, how well does this model fit the data? One can go through the same process again, estimate the path coefficients, and then use those path coefficients to attempt to recreate the correlation matrix as closely as possible. The same fit indices can then be used to measure or describe how well this model fits the data. So we have two models with two different fit indices. Both models say that there's no direct relationship between school readiness and school quality. One model allows for a direct effect between parent education and first grade reading scores. In essence, it allows for parent education to have some effect on first grade reading scores that's not related to school readiness or school quality. The second model is more constrained. It's more restricted and says that nope, parent education has no direct effect on first grade reading scores. It only has an indirect effect through school readiness or school quality. We can then compare the fit indices for the two models, and if one model is a significantly better fit, we choose that one. Note that you can't do this in path analysis using multiple regression. On the other hand, if there's no statistically significant difference in fit for the two models, we go with the more constrained model because it's simpler. It requires fewer paths. And it makes sense to go with a simple explanation rather than one that's more complicated. Looking at these two models, let's imagine that the fit indices were very similar and not significantly different. In that case, we would choose the more simple, more constrained model with no path between parent education and first grade reading. Now, I would be remiss not to note that there are multiple other fit indices that work in a variety of different ways, and this is a pretty simplistic summary of how this all works. But it gives you a glimpse of how structural equation modeling operates and its limited parallel in path analysis via multiple regression. So while path analysis using multiple regression can kind of look like structural equation modeling, true structural equation modeling provides additional useful tools. It allows you to not only estimate how well your model fits the data, but it allows you to potentially compare two different models to determine which of them are the better fit to the data. You can't do that in multiple regression analysis. Now, there are other tools and flexible options that are available in structural equation modeling, but for now, this wraps up our brief peek into structural equation modeling from a multiple regression path analysis background. Thank you.